Today we are going to do section 3.4. So let's first look at the book. This is just the page that was already scanned previously, but I will show it to you again on principle, I guess. Let's see. Okay, that should be good. So next, page 102 and 103. Let me line this thing up in the middle. Okay, that's about it. And then a little bit closer on top. Okay, and a little closer on the bottom. Okay, that should do that. And the last page of homework, page 10 something, 4 and 5. Okay, let's see, that's about as close as I can get. The one corner seems more fuzzy. Anyway, let's now zoom in. Okay, and then look at the bottom. All right, so that should do it. So let's look at the Frenet-Serret formulas. What are they? Well, they're mostly stuff that we've already developed but haven't given them a name for. But first, let's consider the concept, okay? On the bottom of page 101, where we think about the formulas are something that describes the derivatives of alpha, beta, gamma with respect to, in terms of some kind of alpha, beta, gamma. And we'll see, what does that mean? Well, for one thing, then any vector can be a linear, you can break it down into the components of alpha, beta, gamma, being that they are a right-hand system with, all three things perpendicular like that. So, and if you do, then there's a way to calculate it in this case, where if you have this thing, I think pronounced eta, the n with a long tail, and the eta, or maybe something else, I don't really care, okay? Let's just call it eta for now. So eta equals those things, and to calculate what they are, all you have to do is take eta dot alpha, that will give you the first k, the first constant, and so on. Now, so then it when eta then is give me a second here. As it turns out that if we're considering alpha, as we've mentioned earlier, the derivatives of alpha, beta, gamma, that is alpha prime, beta prime, and gamma prime, then there are fairly short simply expressed formulas of expressing these derivatives in terms of torsion and curvature. And so the equations are known as the Frenet-Serret formulas, which is actually the name is longer than the formulas themselves. So let's go to the next page. Okay, now to derive the formulas require a bunch of tiny little equations or manipulations that we've already done, but you might not remember it because they're sort of repetitive, and everything looks more or less the same. So first, we know that alpha is x prime of s, okay, and that is a given fact. That is, the definition or something. And then d alpha by ds, of course, is x double prime. Then the definition of beta, of course, is defined as x double prime divided by its magnitude. But then because of that, and then the curvature is defined as 1 over r, which is the magnitude, okay? With all that information together, and if you stare at this for a little bit, then you realize that all this stuff is true. All this stuff means that, because all these other three are just definitions. Now this one, it end up d alpha by ds is end up being beta, which is then beta getting rid of its denominator, okay? Or you can say beta times 1 over r, which is what that is. Being that 1 over r is the magnitude of x double primed. So and similarly, we can consider next trick that we're going to do, where the gamma prime dot gamma equal to 0. How do we know that? This is something that we've done earlier. That means what you're gonna do is you know that gamma dot gamma equals to 1. Okay, this is something that we did. Let me find it and show you. So I found it on page 95. Okay, now as you can see that on page 95 we have gamma dot gamma equals to 1 always. Okay, so you can take the derivative of this thing at both sides with respect to s, similar to this. Because it equals to 1, then the derivative, which end up being 2 times gamma gamma prime, okay, equal to 0. And that's where we got this thing right here. That gamma times that gamma prime dot gamma equal to 0. Similarly, gamma prime dot alpha equal to 0 because gamma dot alpha is 0. So the prime is also 0. So then from these two situations, however, if you look at it closely, you notice that gamma prime is perpendicular to both gamma and alpha, which means it has to be parallel to beta, okay? Because those three things are orthogonal. As a result, then so we write down gamma prime equals to k beta for some constant k. And then, so then the next equation is that we look at 1 over t. All right, I should probably mention a little better the previous information where I said that gamma prime dot alpha equal to 0. That was already mentioned on page 100 with a page earlier, but I'll just repeat it here. The reason that is 0 is first we take the derivative of gamma of alpha dot gamma, which is being that they're perpendicular, they're 0. So here's the derivative, and then we notice the second part, which happens to be alpha prime is x double prime, right? Dot, this is gamma divided by its magnitude, and then you have double prime and double prime there, which means this thing is equal to 0. Okay, anytime you have a repeated row in the determinant. As a result, then which if this thing is 0, then that thing is 0. Yeah. Anyway, so we have all these tiny little equations that we have to either prove or remember. It would be faster if you do this yourself, actually, but I will go through it anyway. So then the 1 over t is given as gamma dot beta primed. And where do I get this? This comes from a page ago. Okay, it said this is page 100, where it says so on the other side, right here. Okay, 1 over t is gamma dot beta prime. So that's where we got that. And so you see we got all these tiny little formulas to think of. So as a result, 1 over t then equal to the negative. If 1 over t equals to this thing, okay, it also equals to the negative of that. Why? Because if you look at page 100, there's that equation right here, which just means we took the derivative. Okay, there's a beta prime dot gamma plus beta dot gamma prime equal to 0 because you took the derivative of the dot product of beta dot gamma. So anyway, we got here. So after all these tiny little equations, we finally got, because what are we doing? So first we knew that gamma prime equals to k beta. Next we know that 1 over t is equal to negative gamma prime dot beta, right? Which so what does that tell you? That means what is the value of k? The value of k then must be negative 1 over t. All right, I might as well write this down. Well, to see what I just said is 1 over t, okay, which equals to minus gamma prime dot beta, which is, we'll plug the gamma prime, which equals to k beta a little earlier in here, okay, in terms of gamma, and then gamma prime, and then beta dot beta equals to 1, so this whole thing equals to minus k, which means k equals to negative 1 over t. So as you can see, we're doing a pack of tiny little manipulations here. And so as a result, eventually we got gamma prime then, being that k is minus 1 over t, then gamma prime equals to minus beta over t. So by now you might be wondering, what are we doing again? We're trying to calculate alpha prime, beta prime, and gamma prime. So far we did alpha prime, that was given, and then some gamma prime. Okay, so now we need to figure out what beta prime is. So beta prime, we take the definition of beta and do some kind of let's do some substitution because we already know what the d alpha and d gamma is. Okay, plugged it in, and then doing the cross product. Then gamma cross beta is, I don't know, plus or minus 1. You should look it up on page, I think 95. Yeah, it's on page 95. So some these things cross each other equal to, no, it doesn't equal to minus 1, equal to alpha or beta or something. Anyway, so you plug that in. So gamma cross beta equals to minus alpha, okay? And then beta cross alpha equals to minus beta cross alpha equals to positive gamma. And so anyway, so there's that. And then after all this jabbering about tiny little formulas, then we came out with this set of equations. The equation is written, there's nothing here. That's why the dot means nothing, okay, literally. So d alpha by ds equals to beta over r, and then d gamma by ds equals to negative beta over t, and then d beta by ds equal to that. So the author wrote it this way because he thinks that makes it easier to remember. Does it? I don't know. I don't think it makes it easier to remember for me, but you might feel differently, okay? And I think this thing is just, you know, a bunch of tiny little formulas that's super confusing looking. But anyway, it's still nice to have, and you're going to need it for your homework. So next, let's look at section 4.2 on the bottom, where we have, oh yeah, by the way, all those tiny little formulas, please be sure that you go over them yourself, okay? And doing all this stuff. There's more to do, and but you should be able to dig them all out. All of them are something we've already done or almost done. So let's look at section 4.2. Now, being that we have the derivatives, there is a way to obtain the Taylor expansion of a vector. Okay. Now, first let's explain what that means. The Taylor expansion of a vector means that we're going to expand each component of the vector, okay, so that we have 3 components all expanding by the standard Taylor formula, and then we'll summarize them in the vector form so that they are more compact. So let's see what that means, and we can do that because we know certain things, okay. So then we to see the details, let's look at this. Now, first we know that, let's see, we're expanding something, all right? So we need to know what the derivatives are, okay? So x prime then equals to alpha, fine. And remember, this is x in terms of s, okay? That is parameterized by s, the arc length, because arc length is much easier to talk about. And so let's parameterize with s in mind. X prime will be alpha, x double prime will be beta over r. We just did that at some point, and well, yeah, well, maybe right here or something. Well, no, right there. Okay, x double prime equal to beta over r. Okay, so far so good. Then x triple prime equal to that pile of stuff. Now, where did that come from? Please work this out yourself. So I have it done here, okay? So you start at x double prime, which is beta over r, and then you take the product rule of this thing. That is, you take 1 over r as the 2 beta times 1 over r, and take the product rule, and then you will quickly end up like this. And then once you get that, then you substitute beta prime, which is that thing, back in there, and that comes out pretty nicely. And that's x triple prime. And then what about the fourth product? I don't know. I didn't really want to touch it. So we got to the 3 products, and remember what this is. Okay, this is the vectors. The vector, all 3 components individually being expanded by the normal Taylor expansion, and then we compact them in the vector form, which is yeah, and everything works out like it says. So anyway, so here's the Taylor expansion of some vector, okay, which is quite neat. And then if we were to plug in something equal to 0, if we develop stuff as 0, then similar to the Taylor expansion, we have x is 0, okay. Then x prime of times s, and then being that we're developing as 0 is s minus 0, which is just s. And then s squared over 2. Okay, the first coefficient is x double primed. And then x, this is x triple primed times x s cubed over 3 factorial. Now that is, if that looks familiar, because that is the Taylor formula for one variable. But now we are going to apply the same thing for 3 variables. Now the Taylor expansion is on page 43, and then remember what it was. It's the sum of the derivative times the x minus the some point, okay, and then divided by the factorial. And that is exactly what we're doing here, except that we're doing all 3 components at the same time. So we write things in vector form, but the principle is the same. So this is x primed, the first derivative, and then second derivative, and this pile of stuff is the third derivative, as is shown here. So yeah, so of course to do this, you think then you're gonna calculate 1 over r and then 1 over t and 1 over r prime, which might not be a simple matter, but at least it's doable. So and that is that. Now these equations are important, okay? So pay careful attention to these equations and these equations here and here, because some of it you will need it for your homework. So let's move on to page 103, where we study the usual form of a curve. All right, now we're gonna pose something neat. What we're gonna do is we'll pick a point P on our curve. Once we pick a point P, of course P has the alpha, beta, gamma at P, right, in the right-hand system, the 3 coordinates. Now what we're gonna do at this point is we're gonna use the alpha, beta, gamma as the new x, y, and z coordinates, okay, which your book calls it the x1, x2, x3 coordinates, same thing. So then, and so here's a 3-dimensional thing. Now remember, t means alpha, okay, n's the normal, means beta, and then finally b means the binormal, which is gamma. So I made this thing for calculus 3, so I'll show it to you again. So now we're going to use these 3 things as the let's see, well, whatever, as the new x coordinates. Okay, alpha will be x, okay, and then beta here will be y. So that will be something like this angle, right? And then gamma will be on top as z. So that is the new coordinate system. Now, if that is the case, then alpha will be considered 1, 0, 0, right? Beta is 0, 1, 0, and gamma is 0, 0, 1. So at that point, we can rewrite equation 1 on the previous page as in the component form. Now, so what happens here is that we know that alpha is now 0, 0, 1. So x1 is only the alpha coordinate, right? So anything with alpha in there will be x1. So then for x1, then we have alpha s. So alpha being 0, 1, 1, so we have just s there, all right? And then and that's nothing, because that's just beta. And there's another alpha here, so which has what is it, minus r over 2. So we wrote it down right here. See, the alpha equals to let's see, no, as did I see it wrong? Where is it? Oh yeah, it has to multiply. Is alpha over r over 2 better than not? Forget to multiply by the s3 divided by 3 on the other side, which is where we got that. And similarly, the beta one, you just look at all the stuff that has beta here, which is the second term, okay, which is the coefficient of beta is what is that? S squared over 2 or something? Yep, s squared over 2r. That's correct. See, right up there. And then down here, the coefficient of beta is 1 over r times s cubed over 3. So 1 over r, yeah, over 3 factorial right there. And similarly, the x3 will be done the same way to check out any coefficient of gamma, because gamma is now 0, 0, 1. So as a result, you're able to come up with this stuff. But this is with the new coordinate system where alpha, beta, gamma is the x, y, z coordinate system. Now, if you do that, then we will be able to, we'll look at this stuff, okay? And then what we're gonna do is let S1, S2, let x1, x2, and x3, we'll only accept the first term, basically. That is, so we'll let x1 equal to s, x2 equal to s squared over 2r, and x3 equal to s cubed over 6rt. There's more stuff, but we'll ignore it in the neighborhood, in a very small neighborhood of the point P that we're talking about. Now, if we do that, then assumes that the stuff on the denominator is not, it doesn't equal to, well, assume that something, that curvature and torsion aren't 0, okay? Then things get knocked out and we don't know what to do. But let's say that neither the torsion nor the curvature is 0, then we can with a approximation I just mentioned, where x1 we'll just pretend is s, throw away the rest of the stuff, and so on. Then we can come up with these 3 equations, a, b, and c, that you see on the bottom. Okay, and these are what are they? They are the projections on the 3 planes in the. And so please work that out yourself. Okay, basically what you do is you set these 2 equations the same. You can even do it in your head. If x1 equal to s and x2 equal to s squared over 2r, then the relationship of x1 and x2 would be x2 equal to x1 squared over 2r. See? It says right here. So that's, you just set these 2 things the same, and then, get rid of s or something. Well, plug one into the other, something. Okay, solving a simultaneous equation. So that's how you can solve all the others as well. And then you, if you do, then you end up with these interesting curves. And so the equation of this, okay, is some parabola, because this is a parabola situation. Okay, so that it draws it right here. And then remember, these are the projections of the curve onto the various planes. So in other words, the shadows. Okay. So similarly, what is that? Well, whatever that is, the t is that looks something like this, because you're doing is the y this is x to the power 3, right? Yeah, I think that says 3. Yes, it does. And so that's some kind of third power. So it goes like that. And then finally, this equation is. It looks like this, and well, you might think, what happens? How come x is not negative? Because the way the original parameterization has x2 to be always positive, because we're taking x2 equal to s squared. So there is nothing on this side. Okay, the graph looks like that. And so please verify all this stuff yourself. It's a bunch of little details that nevertheless might be somewhat interesting. The concept is. So then eventually, of course, the curve does for B does depend on whether t is bigger than 0 or less than 0, because then it will flip the thing either above the axis or below. Okay, and so please check that yourself. And we have come to the end of this section. For homework, please do problems. I haven't written it out yet. Let me find out. All right, I found it. So for homework, please do problems 1, 2, 4, 5, 6, 7, 11, 12, 13, 14, 15. And when you're done, I want to talk about it. So for homework, let's look at problem 1. Problem 1 is just a matter of getting your chores done. So here are the chores, and I have to write down x. X primed, x double primed, x triple primed, because, well, yeah, I have to write all that stuff down, because x triple primed is required for the torsion, I believe. Yeah, so must have write all the stuff down and calculate what is x double primed, which happens to be 1/2. And then I messed up something here, so keep a look down. X prime cross x double primed, so we look back up there and do the cross product, okay? And pretend that you have I, J, K written on top, and do it that way, okay? Instead of having to write it out again. So x prime cross x double prime equal to that, which is rewritten and then calculate the magnitude, which equals to 1/4. And I confirm that this is gamma, right? Gamma equals to the magnitude of gamma would be equal to 1. So that's just a step to check for mistakes. So anyway, this thing, which is a formula for for the torsion, is equal to all that, and which end up being whatever it is. Okay, so the torsion end up being 1/2, and then of course the curvature is also 1/2. All right. So then I calculate beta based on the information I already did. Alpha is already done up there, and beta is this stuff, and then gamma is this stuff. Now all this can be done. You can do all this stuff if you don't make a mistake anywhere. Okay, the derivative of sine becomes cosine, it becomes negative or positive, and then you need to subtract and multiply and subtract the negative and all that. So as long as you don't mess up any of that stuff, then you'll be just fine. If you do mess it up, then here it is. Here's the right answer, so you can track down your mistake very quickly. So whatever this is, the alpha by ds. Then the next thing we have to calculate, which we confirm to be beta times 1/r. The beta by ds is well, whatever that is, and then the gamma by ds is confirmed to be this equation. And finally, this is the beta by ds, okay, which I calculate up there, but we have to confirm it by using the what is it called? The Frenet-Serret formula? Whatever. So we do that, and I forgot to put a negative sign here, so at first I couldn't get it to work. But eventually I noticed there's a negative sign, so I better change the signs here, and then everything worked out just fine. And it does, everything does confirm like it's supposed to. So that's yeah, did I show you this clear now? Okay, so then you just have to, well, if you don't get it right, that's just because you messed up something, some little mistake like I did. Okay, so so that should be okay. I don't remember if I show you the whole thing properly, so I'll show it a little bit again. All right, so that should do it. So it's just a matter of let's not make any mistakes. Now, then problem 2, I'm not sure why the author thinks it's important to mention problem 2. For problem 2, you just change the formula by changing t to negative t. Okay, as far as I can tell, that's all you have to do, and you'll get the right answer. So next, let's move on to problem 4. And we have to calculate the order of contact. Right? And what was that? That was the distance formula from the curve to the plane in question. But in this case, being that our curve is oriented at the 3 directions are exactly the XYZ axis, the distance then is exactly the x1, x2, or x3 coordinates. As a result, therefore, for the oscillating plane, phi of s is just s3 over 6rt. Okay, and I got that from this thing, from this right here, right? This thing right here, where this will be the x3 coordinates. So that will be the distance to the oscillating plane right here, the first term, s3 over 6rt, and then we'll take the derivative of it. Okay, take various derivatives. Then we go down to, see, x prime, it will be 0 at s equal to 0. X double prime is also 0. Eventually, x triple prime won't be 0. So the order is equal to how many zeros it has. It went up to x double prime. So then the order should be 2. Let's see. And let me confirm this. Yeah, I think I got right knock. That is the contact order is just the highest derivative that becomes 0. In this case, is the second derivative, therefore the order is 2. Similarly, for the rectifying plane, the phi of s, the distance formula is s squared over 2r. Again, that comes from that equation here. Yeah, the first one. Okay, now the equation has more than 1, but we don't care about anything following because then s is even higher power, so they will just go to 0 anyway when you take derivative. It's the first one that matters. The phi of s will be the middle formula, which is s squared over 2r. And having said that, then we'll take the derivative and quickly notice that notice that the order will be only 1 because it's not 0 after the first derivative. And then finally, the normal plane, the order is 0 because 5s is just s. And in that case, in the no derivative, does it go to 0? So it's just 1. And okay, so that is okay. Next, let's look at problem 5, where it says the curvature of something is always 0, means the curve is a line. So if the curvature is 0, all right, we then calculate that curvature has to do with the d alpha by ds in the first formula, I think it is. Well, anyway, if the curvature is 0, then d alpha by ds, which is x double prime of s, is identically 0, which means x, the first derivative, then has to be equal to a constant, which means the function itself must be equal to rt plus a, okay, in 3 forms, which is a line. So that should do it. And next, let's look at problem 6. We're talking about the center of curvature of a curve, okay? And we're giving the definition. The center of curvature is where the curvature has the from the direction of the normal, where the curvature goes, and has the length of r at that point, where 1 over r is the curvature, which means r is the radius. And so therefore the center is going along the beta direction. All right, so that makes sense. And so then we are going to show the locus of the center of curvature, that helix, in example 1. Okay, so from example 1, we already did example 1, where we found out that x double prime magnitude is equal to 1/2, okay? And then beta is defined as is equal to 4 times 4x double prime. Then beta r is equal to 8 times x double prime. Therefore, the locus is going to be x plus 8 x double prime. When you plug in x from the formula of what's x and what's x double x, then you end up with this equation, which is a helix if you type it into the Desmos calculator, which is what I did. Well, anyway, that should be that. I don't care about helixes that much. I find them, they're okay, not that exciting. And next, let's look at problem 7. Show that the center of curvature of space curve 2 is the same as the center of the curvature of the parabola A. And what are they talking about? This is talking about just the previous page, okay, where we have space curve 2, that's represented by these 3 things. And then parabola A is this thing. Now to calculate this, to prove that statement, then we're going to calculate the center of curvature of both. Okay, the first thing is, so the center of curvature, as defined by what that says, is, is equal to x as 0, okay, which is 0 in this case, plus beta times r at that point, where beta is 0, 1, 0, which means that the curvature is, the center of curvature is at 0, r, and 0, okay, r 0. The center of parabola, given by this equation, we'll call it this thing, right? And then if we take the derivative, and then take the derivative again to calculate its radius of curvature, we notice that it happens to be the exact same, end up having the same value. This is the same as that. So they have the same center of curvature. So that's that. Next, let's look at problem 11, which says, let me first figure out what it says. Okay, for the curve shows that alpha prime dot gamma prime equals to something. Okay, alpha prime dot gamma prime, what is that? That is, okay, I think I just wrote down that Frenet-Serret formula, whatever it is, and you plug it in and it equals to exactly that, okay, a one-line answer. So let's look at problem 12, x prime dot x triple prime. Similarly, I've plugged in the formula for x triple prime from this thing right here. X triple prime equal to down here. Okay, see, and let's see. Here's the formula. See next to my finger there. X triple prime equals down at the bottom, right? So I plugged in that formula, in here. So alpha dot all that stuff, which remember alpha dot alpha is 1, alpha dot beta and alpha dot gamma are both 0. So then I got this answer right away. Is that what we're looking for? I think so. Right, I can't turn the page. Right, that's it. And so next, let's look at problem 13, which says we need to use exercise 14 in the previous section to prove something. So we have, okay, from the previous problem, we have gamma equals to this stuff right here, okay? And then we will plug in the formula for 1 over t, the torsion, to be that thing. So then it end up being this, is 1 over t x double prime over its magnitude, which is beta. So minus beta over t is that should be the answer, okay? Another one-liner. How nice. And so problem 14, we will have used the expression for beta prime on the previous homework. No, on the homework in the previous section. And the definition to show that, we need to show basically alpha dot beta prime equals to -1 over r and the other thing. So one thing at a time. So we need to calculate alpha dot beta prime. That would be, I think that's from the previous problem. Okay, it says something about this, about beta or something. Yeah, that's the beta given in problem 13 in the previous section. So I wrote it in there, and then that is, it becomes this is the, let's see, I can't remember where I got this. Let me think. Right, the triple cross product. And so I did the triple cross product right here, okay, in here, which on page 64, which give us, turn the cross product into some kind of dot product, make it much easier, whereas my x prime is still outside. And the next step, this will be equal to just the first part of the dot product. The reason is because the second part has a repeat of x double prime in there, which makes it 0, okay, the dot cross product, which equals to the determinant. So if you have two of them that's the same, then it's 0. So we only have the first part left, which cleans up to be, we have, and I can't read it. Okay, I got it. So it cleans up to be, okay, so there becomes x prime dot x triple prime over there, okay, which I wrote down here. And x double prime dot itself is the magnitude, right? And then there is a dividing by x double prime, which I wrote down here. So we end up with that thing. And what is that thing? By problem 12, we already calculated that, what is that? X prime dot x triple prime is equal to, divided by magnitude equals to 1 over r squared or something. Yep, right here. See, the last problem, the problem 12, if we show that x prime dot x triple prime equals to -1 over r squared. And therefore, so I wrote down the -1 over r squared. Let's see, divided by only one of them. Well, anyway, so then that's that, and times r, which is equal to -1 over r. And the reason for that is because r is 1 over x double primed, okay, which I've written right here, see? And if you think about this a little bit, it all checks out. So that's problem 14, I believe. And then what's this? Oh, the second part of problem 14, then we're supposed to calculate gamma dot beta prime, okay, that's supposed to show up to be 1 over t. So let's do that. Now for gamma dot beta prime, I wrote down the definition of gamma, and the other thing is beta prime from the previous problem. And then, yeah. So once I wrote it down, we'll apply the Lagrange identity on page 64. And I wrote down, this will be my r cross s dot t cross u, right? And then apply that identity. And then you notice the second part is 0 again, because we have x prime cross x double prime dot x double prime. So we have two identical things in the determinant, which makes it 0. And this is on page 64. So then only the first part is left, and so that cleans up to be this, okay, because we have x double prime dot x double prime here. So that cleans up to be this, and that's exactly the 1 over t, like we want. And that the formula is from page 99 of theorem 5. So that is what it is. So next, let's look at problem 15, which says, okay, for this curve, we need to show the x prime dot x 4 primes, okay, which we did not calculate for good reason. I wouldn't want to do anything with it. But now we have to show some dot product equal to that thing that looks pretty simple. So what we're going to do is we're going to take problem 12. Okay, here's problem 12, which we have calculated that x prime dot x triple prime equals to that thing, right? And we're going to take the derivative of x prime dot x triple prime, because then we'll be able to come up with x 4 primes. So that's the plan. So from problem 12, we got this equation, all right? And so we're going to take the derivative. Once we take the derivative, apply the dot product rule, okay? And then take the derivative of that thing. Now, be careful when you take the derivative of that thing. What we want is keep it as 1 over r. That is, we're not going to take the derivative of r itself, okay? In other words, wrote down a quick explanation up here. Let 1 over r equal to u. And then we are taking the derivative of 1 over r minus 1 over r squared is the same as minus u. Okay, then you take the derivative of minus u by ds, you get minus 2u du ds, right? Which is what this is. Okay, so minus 2u, okay, and this is du by ds. So that's how this works. And there is no power here. Okay, you're not doing the, well, because you're not taking derivative with respect to r, but only 1 over r. And because that is how the answer looks, so we're gonna, that's why we do that. Anyway, so then we have, what do we have? So we have this thing equals to that, okay? And what we're looking for is this thing. So we need to figure out what this is, right? And then do a subtraction. So what is that? And let's calculate that. That's x double prime dot x triple primed, which we did calculate at one, or at least the book did at one point in the previous page. Okay, and this is on the previous page where, what page is that? 102. And then see, x double prime is right here, and x triple prime is right here, all the stuff. So let's write all that stuff down and take the dot product, which is easier than it sounds. The reason is because we have a bunch of beta, alpha, and stuff dotting each other. Beta dot alpha is 0, beta dot beta is 1, and beta dot gamma is 0. So the only thing that's left is that, okay? 1 over r primed and 1 over r, see? And then, so then we will do the subtraction. This thing equals to what's on the end here, which I wrote down here, subtracted by that, okay, which is this stuff. So we'll subtract by that, and then very soon you get the right answer, see? That right answer comes out very nicely. So that is the end of this section.